Good evening. My name is Karthik.
And I'm Laura.
And together with my teammates, Daniel and Kibrom, who are in the audience, but I can't quite see at the moment, we're here to tackle space weather challenges and how they affect our society today. So before we get started, here's a quick question, and let's hear some hands if you can answer these questions. How many of you guys here used your phones to navigate to the auditorium today? Or have used, okay, that's good. How many of you guys have taken a flight in the past 6 months? Flown anywhere? All right, cool. Have you guys seen the self-driving cars around Mountain View? All right, you guys have seen it. All right, cool. The reason I asked this question is underlying all of these things that are almost commonplace in our day-to-day lives is a crucial piece of technology. It's the Global Positioning System, or GPS, as we call it. Many of you are familiar with its applications in some obvious ways. You might also be affected by it in some not so obvious ways. There's some estimates that say there's about 3.5 billion GNSS, or GPS-enabled devices that exist. That was a few years ago. That number is going to double over a period of 5 years, so up to 7 billion devices that are GPS-enabled. So our society is increasingly dependent on GPS in many ways. And space weather is something that affects GPS. And the challenge is to find out what affects GPS and how we can mitigate the risks associated with it. So what does affect GPS? This is something that Dr. Lika touched on. She showed a very good graphic about space weather. The image shows our sun. We live in the presence of an active star. It has its own dynamics. It's a complex system. And it produces these huge emissions of energy that affect us here on Earth. So radiations, particles, they propagate outward in space. And they affect us down in the Earth, where it interacts with our magnetic field and the geospace environment. And it affects the technology that we have been building. So the technological infrastructure that we've been putting in place is affected by the space weather. So the energy from the sun affects our geospace. These effects are called space weather effects, and they affect our technology. The question that drove this FDL challenge was then, how can we mitigate the effects of space weather on our lives? So to give you an example, this is what a GPS system looks like. So you have a system of satellites that is orbiting the Earth, and you want to find out where you are. So the ground-based receivers that you have in your pocket, for example, in your phones, they communicate with these satellites. And using radio signals that propagate between the ground and the satellites, the device on the ground can find out where it is. Now, these radio signals, they propagate through this interesting portion of the atmosphere called the ionosphere, which is charged in nature. And as radio signals pass through this ionosphere, they can get disrupted if the ionosphere itself is disrupted. So the ionosphere is dependent on space weather. It's influenced by space weather. And the signals can get affected by it. So when you have space weather events happening, the ionosphere can get disturbed, as a result of which the signals get distorted, and you have degraded performance of the GPS system. So you're no longer quite sure as to where you are. You might have an accuracy of a few meters when it's optimally operating, and that can get degraded when the ionosphere is disturbed. In some cases, the signal never makes it down to the Earth, in which case you have no idea as to where you are. And you might ask, so what's the big deal if that happens? Well, that event, known as ionospheric scintillations, can cause that to happen, right? And you don't want that to happen. So the question that motivated this FDL challenge was, can we use data-driven techniques to forecast GPS disruptions? Laura?
Yeah. So yeah, this is a great question. And hopefully by the end of this, we can prove to you that this is what we were able to achieve. So going back to this Sun-Earth system, it's very complex and nonlinear in its behavior. This makes the predictions of it very, very difficult. To date, there is no current physics-based model that can describe the state of the ionosphere caused by space weather effects to the temporal and spatial scales that we need to be able to predict GPS disruptions. So one potential solution to this is to use a data-driven approach. So we want to look at all aspects of the system, and can we use the data that we can attain from all these aspects to kind of build into a predictive model. So to begin, we need to look at the origin of space weather. The sun. So the sun is the ultimate source of when we talk about space weather. So we need to use solar data in the form of satellite observations, including kind of increased radiation, solar wind, and flux. Following this, we need to know, well, how is this affecting the Earth? We need to look at the geospace of the Earth, the region in which this space weather interacts with the Earth's magnetic field and causes effects in the terrestrial atmosphere. And finally, we also need to look at, that's a hint ahead, we also need to look at ionospheric data. What is the current state of the ionosphere? What is going on at the moment in order to be able to predict what's going to happen in the future and how the signals of GPS are going to propagate through that? So all of these data together hopefully can provide a predictive model. There's no one part of this data that can tell us a GPS disruption is going to occur. There is going to be this type of ionospheric condition. However, if we mitigate these all together, we can use machine learning techniques and different approaches to hopefully be able to build a predictive model. And that's what we did as a team. So in particular, what we focused on was looking at high latitude regions. These are regions that are more susceptible to space weather than other places on the Earth. We used a network of 13 ground-based receivers that see satellites all above the sky. And we needed to use data from these receivers together with our geospace, solar, and ionospheric data to build a predictive model. So how do we go about doing that? We started at a baseline classification problem. What is the chances of some disruption happening above a certain level? So we used our data together with our GNSS or GPS receivers to kind of build this classification baseline, using all the receivers together to build one predictive model. And this worked very well, and we were able to set a baseline. Building on this, we said, okay, what happens if you try to build each local model for each local station? And what we actually found was that you can boost forecasting metrics by building a model for each individual station. And this is very interesting. This is telling us that data-driven machine learning approaches is telling us something about the localization of these space weather effects. So once we found this, we said, okay, well, let's focus on each individual stations. And let's look at what further data do we need to be able to predict GPS disruptions. What we did is we went back, we looked at each individual station, and also included co-located magnetometer data at each individual station. Including in this, we tried to incorporate more parameters into what is going on in the system. Is there a time delay between the coupling of the solar wind and the geospace and the ionosphere? So we looked at different input parameters and feature engineering to try to get a scientifically driven approach to be able to predict, to make a predictive model. Following this, these classification baselines, we wanted to build a more scalable approach. And a scalable approach means using things like a random forest and gradient boosting, and in particular neural networks, to be able to train on large amounts of historical data that we had, together with our large amounts of input data, to actually see, can we forecast GPS disruptions? So what we did is we used 3 years of data from 2015, 16, and 17. We trained on 2015 and 16, and we were trying to test 1 hour predictions into the future in 2017. And what is our breakthrough? We found that we were actually able to use machine learning approaches to our solar physics and geospace data to be actually able to predict GPS forecasts into the future. What we see on this plot in blue is the actual ground truth. This is the disruptions that we saw, and in the red is what we were able to predict. So just to kind of give you an idea, this improved baseline forecasting abilities by 70%. So it really is a proof of concept that you can really apply AI and machine learning to the large amounts of data we have to go forward into the future to build predictive models of GPS disruptions. So what are the outcomes? This is really a proof of concept. We were able to develop a machine learning framework for predicting GPS disruptions. Furthering this, we found that we can actually look at, even though space weather is a global phenomenon, the disruptions that it causes in the ionosphere and in the near-Earth environment can be very, very localized. And again, we improved our baseline forecast by 70%. So this is only scraping the top of the barrel of what can be done by using machine learning approaches. So we went from this to this. So just to conclude, if I can get there, FDL has given us an opportunity to bring scientists and researchers from all different interdisciplinary fields together with resources we would never necessarily have, and use scientifically driven thoughts and ideas to actually, and use them with machine learning approaches to actually curate new ideas into the future. And going forward in society that we're becoming more and more susceptible to space weather, this is the way forward. Thank you very much.